Solving the Traveling Salesman Problem Using a Genetic Algorithm by Sanjaysugumar. A genetic algorithm is a search and optimization method inspired by the processes of natural selection and biological evolution. The genetic algorithm has 5 components: population, calculating fitness, selecting the best genes, and crossing over and mutation. The fitness function calculates the total distance traveled in a route and returns the inverse. Higher fitness means a shorter route. The random choice function selects a random choice from the population. Routes with better fitness have a higher chance of being picked. The crossover function is responsible for the reproduction of 2 routes. The 2 routes are split at 2 random points compared to the 1 random point shown in the textbook and spliced together, creating a new child that is a combination of the 2. The mutation function will randomly pick 2 cities in a route and flip them. This introduces randomness for getting out of the local optima. This is the function all put together. The population is initialized with random routes. The algorithm then repeats for n generations. Within each generation, the fitness values are calculated for the population. The algorithm then finds 2 routes and does a crossover. This new route then has a chance to be mutated and then is added to a new population set. The best generated route is stored and compared to the best route across all generations. This new population set is then used for the next generation. After n generations, the best global route is returned. Now let's walk through some test cases. The first case is with a manageable amount of cities with the distances randomly generated. The algorithm performs well and finds an optimal solution. The next test case is one where there is a clear path to the cities that is better than the others. The algorithm correctly identifies this route as expected. The next test case and the following follow the dataset with a larger amount of cities. This algorithm performs well and finds an optimal route, proving that the algorithm is scalable. The next test case uses a higher mutation rate of 0.5 from 0.25. This means that the algorithm is less prone to getting stuck in local optima. This algorithm does find a slightly more optimal route. This test case uses a much lower population size of 5 down from 100. This means that there is lower diversity in picking an optimal route. This algorithm does find a less optimal route as there is less variety in picking samples. This test case involves a much higher amount of generations. This means that the algorithm has a better chance of finding an optimal solution. As expected, this algorithm performs very well but is computationally expensive. For the first edge case, we are testing identical distances between each city. This algorithm doesn't get confused by identical distances. The final edge case is one where the algorithm can be shown getting stuck in local optima. When run with a low number of generations, mutation rate, and population size, the algorithm does not converge on the optimal solution of around 200. Thank you. Have a nice day.